All right, it's 11 o'clock. We'll go ahead and get started. First thing you see written there is just announcement. As of right now, unless something unexpected happens, which these days is always possible, but right now we're going to plan on having our second test. Uh, Tuesday, July the 7th. Also remind everybody this will be at 11 a.m. So at our regular scheduled class time is when we'll take the test. And I know it's Monday, but at least one thing to look forward to this week. It's a short week. We just have class through Thursday. No class this Friday, and then we're off the whole following week for 4th of July. So got a pretty good break in there. But our test will go up through section 5.5. That's the last thing we're going to do in chapter 5. And then, so that, just make sure everybody's aware. Plan on that for now. Now, before we get started working any problems, just remind everybody last Friday, we were talking about twisting circular shafts. So if we've got a shaft with a circular cross section, yeah, not too bad. And we apply some torque, this twisting moment we call torque, to this shaft, which has a radius, be consistent with the notation the book uses. Uses a little c for the radius of this cross section. We saw that this causes a shear stress, and the maximum shear stress is going to be located on that outer surface. And the formula that we derived was Tc over J, where T is the applied torque to that section, C is the radius, and J here is the polar moment of inertia. And for a circular area, J is pi over 2, that radius to the fourth. And so that's basically what we spent Friday doing, was developing this formula for shear stress. What we're going to do next here in just a second is we're going to work a problem and see if we can apply that and calculate the maximum shear stress. Any questions related to this formula before we see if we can solve a problem? All right. Well, then let's continue and see if we can solve this one. We're going to try to find the maximum shear stress, and sections A, B, and BC. So let me see if I can draw a picture of this shaft. Part of it's hollow, part of it is solid. So yeah, we'll see. This may not come out too good. I don't know. I'll try my best. I've done work. This left end is fixed. It's attached to the wall or something back there. This is this end called A, B, and this end C, and some dimensions. AB is solid. It's 2 meters long. And then the end BC here, the hollow part, is 3 meters long. And mine kind of looks like it tapers a little bit, but it's the hollow part it's the same size all the way down. It's got a 40 millimeter diameter. The solid part back here's got a diameter of 60 millimeters. Let's see. So I think I've got all my dimensions, and there are 2 torques acting on this shaft. There's a torque here at this end, acting in this direction, 2,000 Newton meters. And then here at B, there's a torque in the opposite direction. It's twisting it this way, 6,000 Newton meters. All right, so that's what our shaft looks like. Starting at the outer end here, C, it goes in 3 meters. It's hollow, and the the hollow part's got a diameter of 40 millimeters. And then from that point B back to the wall at A, it's 2 meters long, and it's a solid circular cross section with a diameter of 60 millimeters. And we're applying these 2 torques to the shaft, and our goal is to try to calculate what is the maximum shear stress in the solid section back here, AB, and then again out here, the hollow part between B and C. All right, any questions about my picture? It's not great, but hopefully it's clear. Everybody sees what the shaft looks like and the 2 applied torques in the direction. All right, so in order to solve this, right, we need to know what the torque is in each of those sections. We need to know what the torque is in section BC to calculate the shear stress in BC. We need to know what the torque is in AB in order to calculate the shear stress in that section. This is very similar to when we did shafts that had axial loads applied. For example, maybe we had a shaft, we had several different loads apply, right? And to get the normal stress in each of those sections, we had to do method of sections, come in here and cut it, and find what the axial load was in that particular section in order to do normal stress P over A. Well, the exact same concept works here, except now instead of getting axial or normal load P, we got to get the torque in each section. But how we accomplish that is the same as it was with the axially loaded shaft. We're going to have to cut this. We're going to do method of sections. We'll cut it somewhere between B and C, see what the torque is in that section. Then we'll come back here somewhere between A and B. Cut it there. See what the torque is in that part of the shaft. Right? So very analogous, I don't know if I said that right, to what we did with the axial loads. We're going to now do with the torques. So it doesn't matter which one we do first. Let's just start out here with section BC. So we're gonna cut it somewhere between B and C, and so I can draw this picture. So if we cut it here between B and C, just like we did with the axial loads, you got to draw a free body diagram of all of the left side or all of the right side. You can get there either way. Here, there's more work if we do the left side, because one, we would have to determine there's going to be some reaction torque here, right? The support reaction where this thing's fixed to the wall. There's going to be a reaction torque there. We'd have to calculate that. And there's more stuff over there, so it's less work to look at the right side here. So we cut this somewhere between B and C, and we draw everything to the right of that. So what we have is we've got a 2,000 Newton meter applied load, right? So if we're looking at just everything to the right of that, that's the only applied torque over there, right? That 6,000 is between A and B, or at B, but we're cutting it between B and C, so it doesn't show up. And what we need and want to know is, what is this torque? We'll call it TBC. So we're looking at this free body diagram where we cut it between B and C. That's all we have to the right of where we cut it. Well, the torques have got to add up to 0. I think hopefully, anyway, everybody should be able to just look at this and tell me and conclude that what the torque between B and C has got to be 2,000. All right. Just from observation, torque's got to add up to 0. Well, we've got a 2,000 Newton meter torque going this way. We've got to have 2,000 Newton meters going the opposite direction, so the torque's add up to 0. So that's the torque in that part of the shaft between B and C. Any questions how that torque was arrived at? All right, so let's get our maximum shear stress. In section BC is just going to be again, TC over J for section BC. Well, we just determined what the torque was. C is going to be the outer radius, and J is polar moment of inertia we'll calculate. So this torque is 2,000 Newton meters. C, this C is not the same as point C. This C in this formula is this outer radius. And that would be, I think, 30 millimeters would be the radius from the center out to the outer surface, which be careful, make sure units compatible. These are Newton meters, so we want our radius in meters. So that's 0.03 meters. And to get our polar moment of inertia, the pi over 2 c to the fourth, that's for a solid, right? We have a hollow tube here, so we've got to take the polar moment of inertia for the big circle and subtract the polar moment of inertia for the inner circle. So we're going to get pi over 2, the outer radius to the fourth, which is 30 millimeters or 0.03 meters. And then we're going to subtract the inner radius, which the inner radius would be here to here. That would be, that's pretty small. Maybe you can be 20 millimeters, right? The hollow part's got a diameter of 40. So the radius is 20 millimeters or 0.02 meters. And we subtract that. And that should give me the maximum shear stress in section BC. And I got what 58 million something, so I just rounded it to 58.8. These would be megapascals, 10 to the 6. Right? So that's how we get maximum shear stress in that part of the shaft. Any questions for section BC? All right, well, we're going to do very similar, exact same process to get the maximum shear stress in this part back here, the solid section AB. We're going to, as I mentioned a minute ago, we're going to cut it somewhere between A and B. And so if I can draw this free body diagram. Again, I'm going to go everything to the right of where I cut it. So if we cut it here between A and B, I'm drawing the free body diagram of everything to the right. I got to go all the way to the end. Can't just take a little piece out of the middle. But that's where we're going to cut it. Again, this was C, this was B, and then we cut it between A and B. And we had 2,000 Newton meters in that direction. And here at B, we had 6,000 in the opposite direction. And we want to know what is this torque? Call it TAB, torque section of the shaft between A and B. But if necessary, you can write down the equation, but hopefully this one, again, is pretty simple and straightforward enough. If the torques have got to have to 0, what's the torque AB got to be? Somebody chime in or type in the chat.
4,000.
Say that again?
4,000.
That is correct. Right? We got 6,000 going this way. It means we got to have 6,000 going the opposite direction. Well, I got 2,000 here, so I need 4,000 there, so that I got 6,000 going each direction. So this is going to be 4,000 Newton meters. Again, if you need to, define one way or the other positive, write the equation down, set it equal to 0, and solve for that unknown. If you got to do that to get it right, do that. But most of these, especially if you draw the free body diagram, again, I can't emphasize importance. Draw the picture. Right? You're going to get this correct more often than not if you draw the picture. Right? But any questions how we got the torque between A and B to be 4,000? All right, well then we'll do the same thing, right? To get the maximum shear stress in section AB, we'll just do TC over J. And for section AB, we just calculated the torque is 4,000. C, again, is the outer radius, and back here between A and B, the diameter is 60, so the radius is going to be 30 millimeters, 0.03 meters. J, this is solid back here between A and B, so we don't have to do what we did for BC. It's a solid, so it's just pi over 2, the outer radius to the 4th, so 30 millimeters or 0.03 meters would be J for that solid section AB. And then again, take out your calculator, calculate, I got 94 million something, which again, we're going to write that as 94.5 megapascals. Nothing wrong. If you want to write out 94,500,000 something pascals, you can do so, but most people would prefer to just write it as 94.5 megapascals. Right, so that's going to be the maximum shear stress in this part of the shaft back here between A and B. So anywhere between A and B, that's going to be the maximum shear stress. It's going to always occur at the outer surface. That's where you're going to reach the maximum shear stress, always outer surface. Right, any questions how we got the maximum shear stress in that part of the shaft?
Yes. Why for BC do we subtract like 0.3 to the fourth minus 0.02, but we don't do the same thing for AB?
Because BC is hollow. When you look at the cross section for BC, let's see, stick it in here. It's hollow, right? So we want the polar moment of inertia for this area. So,
Okay.
so to get J, you're going to take the say for the outer minus the inner. You're subtracting the moment of inertia of that whole. Whereas when you look at AB, it's solid.
Okay, that makes sense. Thank you.
You're welcome. All right, good question. Any other questions? All right, everybody got this written down? Okay, move to a new page. No one objected? We'll turn the page. All right, so sort of special little thing we're gonna include here is in section 5.3. Talks about power transmission. Shafts. Kind of special topic here. But this is a fairly common place where you see circular shafts being subjected to torques. Is to use to transfer power from one device to another. You see these a lot in motors and engines. Your car has a transmission shaft. It transfers the power from the motor to the axle, makes the wheels go. And more often than not, these are going to be circular, and more often than that, they're going to be hollow tubes, because we discussed this earlier. I think Friday. The shear stress right in the center is zero. So if it's a solid cross section, that material right in the middle is really not being stressed at all, and so it's you're carrying around dead weight. You don't need to have that solid shaft. You can get just as strong, just about, if it's hollow, using a lot less material, and it's lighter. But that's what this section focuses on, and really you need one relationship or formula here, and that is that power. And you probably saw this in physics, but capital P for power is equal to torque T times omega. So again, this is a lowercase Greek letter omega. It's the angular velocity. So again, P here is power. T is equal to the torque. And omega here is the angular velocity. it's how fast this transmission shaft is spinning around. Um, torque here is going to be in either Newton meters or if you're doing English units, foot pounds or pounds feet. It doesn't matter which one you say first or what order you write it in. Very important though, if you're going to use this formula, your angular velocity here has got to be in radians per second. Now, if you read through this section in the book, you're going to see some additional formulas. He talks about frequency, which is revolutions per second, and he comes up with a couple of other formulas that relate power and torque and frequency. If you want to use those formulas, and you're welcome to do so, but I wanted to mention and point out I am not going to use those formulas simply because, one less or two less formulas I have to worry about, the better. And this formula is really all you need as long as your angular velocity is in radians per second. Personally, me, I would rather convert, if I'm given angular velocity in something other than radians per second, I just convert that to radians per second and I use this formula, right? Again, if you want to, those other formulas you'll see in there allow you to put in an angular velocity in something other than radians per second. So your choice. You can memorize a different formula or just convert omega to radians per second. That's the approach I'm going to take. Now, for power, the units. All right, so if they're SI units, torque is going to be in Newton meters. If omega is in radians per second, you get Newton meters, radians per second, but radians dimensionless. So you're just going to get Newton meters per second. Now, in the SI world, that's called something else. Anybody, kind of like, when we're doing stress, newtons per meter squared, we call it a Pascal. Anybody remember what Newton meter per second is? What's it called? Somebody? Kaylee, yay, a watt. That is correct. So this is called a watt. So typically, if you're doing SI units for power, they're referred to as watts or kilowatts. But it's a Newton meter per second. Right? So as long as you know a watt is newtons meters per second, you're good to go there. Now, in English units, sometimes the English units do strange things, but if you're doing English units, you're going to get pounds, feet per second. But you almost never see power given in foot pounds per second in English units. Somebody think of one. What do you typically use for power if you're doing English units? Somebody other than Kaylee. Kaylee she did the watts. Now, I know there's a bunch of guys out there who drive cars and
Horsepower.
Horsepower. There you go. So 1 horsepower is equal to 550 foot pounds per second. Again, this is horsepower. So typically that's what you'll see power given in if it's English units. You'll say this thing's delivering 2,000 horsepower. Now, you need to know what the conversion between horsepower and foot-pounds per second is. All right. So that's all we need to solve any of these problems related to power transmission shafts. Any question at this point before we work a problem? All right, well then let's see if we can do this one. We are told that we've got an engine that delivers 200 horsepower to a drive shaft everything right, that's turning at 1140 RPM. We're told the allowable shear stress is 8 KSI. The outer diameter is 2.5 inches. And we want to find the minimum required thickness of the shaft wall. So we've got this drive shaft. Obviously, it's a hollow tube, and this drive shaft is rotating or spinning around at 1140 RPMs. It's delivering 200 horsepower. Whatever the material that it's made out of, where we're given an allowable shear stress. Our shear stress cannot exceed 8 KSI. How thick does the wall of this tube have to be so that we don't exceed that shear stress? And maybe not absolutely essential, but picture never hurts. So if we look at the cross section of our drive shaft here, the outer diameter we are told is 2.5 inches. And what we're asked to find is what's that thickness got to be? Right? If it's too thin, our stress will be too large. And again, we could make it really, really thick and have a stress lower than that. But again, in the engineering world, you want to always try to optimize. You don't need to make it thicker than is necessary. But that's what we're after. What we're asked to find is what's the minimum thickness in this wall so that we don't exceed 8 KSI. All right, so we've got to do a couple of conversions here. One, the 200 horsepower, we need to get that in foot-pounds per second. So the power is going to be 200. Again, these are horsepower. And so we're going to multiply that times 550. These are foot-pounds per second. Is 1 horsepower. So our horsepower cancel. And now we have the power in foot-pounds per second. Comes out to be 110,000. Right, so that's what 200 horsepower is equivalent to. And using the approach that I mentioned a minute ago that I said I was going to do, if we're going to use this formula, how fast it's spinning has to be in radians per second. So we need to get our angular velocity omega in radians per second. So 1140, those are revolutions per minute. That's what RPM stands for. And so we just got to convert that to radians per second. Well, 1 revolution is 2 pi radians. 1 revolution, 360 degrees, or 2 pi radian. And as far as we need to get minutes to seconds, 1 minute is 60 seconds. And if we multiply this out, we'll now have our angular velocity in radians per second. Right? Minutes cancel, revolutions cancel, we got radians per second. I got 119.4 radians per second. Again, here's where I think there's maybe one of those other formulas in the book might be for where you could put in, say, omega and RPMs. But then you got to know another formula. I would just prefer doing this, convert omega to radians per second. I don't have to remember a new formula for that. And then plug it in this formula. Power equals torque times omega. So we got the power, we got omega, we can find the torque. So we got 110,000 foot-pounds per second. That's equal to torque times 119.4 radians per second. Solve for T. This will be the torque in foot-pounds. And I got 921.3 foot-pounds, pounds-feet. That's the torque that has to be applied to this shaft to make it rotate at 1140 RPMs and deliver 200 horsepower. And so now we've got the torque that's acting on this shaft. Any questions how we got the torque? Right. So that's really I reckon the new part to this problem. Now it's right. We're going to use same formula we used in the first problem. I know tau max is equal to TC over J. So we're going to set this equal to our allowable, our 8 KSI. We know the torque now. And then C is the outer radius, which is half of 2.5. And then J, we're going to have to calculate the polar moment of inertia for this hollow cross section. It's a hollow tube, just like we did in that section. I think it was BC in that previous problem. So tau max, we're going to set, and be careful again, units. That's a KSI. My torque is in pounds, not kilopounds. So I got to do one of two things. I either got to get this in kil feet, or I got to convert the 8 KSI into PSI. I'm going to go with the 8,000. Again, this will be PSI, pound per square inch, since my torque over here is in pounds. As long as they're both the same, you're good. The torque is 921.3. Now those are, again, pounds feet. This is pounds per square inch. So again, we got to be careful with our units, and they need to be compatible. So if I want to convert this to, instead of pounds feet, I really want it in pounds inches, since this is in per square inch on all the lengths in inches. So we got to multiply that by 12. Again, the reason for that is I want pounds inches, not pounds feet. C, that's the outer radius. So it's half of the diameter, so half of 2.5 is 1.25. Now J, for the hollow tube, we've got to, again, do pi over 2, the outer radius to the fourth, minus pi over 2, the inner radius to the fourth. I'm just going to factor out the pi over 2, and we get the outer radius to the fourth, which is 1.25 to the fourth, minus the inner radius to the fourth. So this is the call it RI. That is what we don't know. That will depend on the thickness. All right, so does that look, I got everything in the right place? My units all are good. Again, these are inches. I got this in inch pounds. This is in pounds per square inch. So all my lengths are inches. And then again, I'm going to skip going through the algebra, but that's what we're solving for. Solve for the inner radius. I got just over 1 inch. I got 1.076 inches. But now we can get the thickness, because I know the outer radius is 1.25, so the thickness, I just take the outer radius minus the inner radius. 1.25 minus 1.076, 0.174 inches. So it's a good illustration to show that doesn't have to be real thick. That's pretty thin. And you'll find that's the case. That's why you don't need, all of that material, that big hole in there is material we don't need. Right? We can design the shaft so that it does not exceed 8 KSI. We don't need a real thick wall to do that. All right, questions about this one? There's some good examples in the textbook, similar to the two we worked here so far today. Certainly encourage you to look at those. Last chance. Any questions on this one? All right. Does anybody need a few more seconds to finish writing anything down, or has everybody got it there? Assuming that means you got it. Well, just a couple of minutes. We might wrap up a few minutes early today. I'm just kind of give you about a 2-3 minute. Where we're headed tomorrow is the next section talks about the angle of twist. So up to this point in chapter 5, it's focusing on shear stress. In this section, we're going to study and explore deformation. When we apply a torque to this shaft, how much does it twist? What angle does it rotate through? And that's what this section's about. And basically, all I want to do is just kind of remind you, we actually came up with this formula on Friday when we were deriving the formula for the shear stress. I told you that I wanted to go ahead and show you where the formula for angle of twist comes from, while we had all that stuff fresh on our mind. But the angle of twist, notation-wise, this book uses phi. And if we apply, let's say we got torque going this way. So we're going to twist this thing. When you look at this cross section, the angle that, and I'm drawing this, greatly exaggerated. We talked about, in fact, when we derived this formula that I'm fixing to write down, it was only valid for really small deformation. And so if you actually have an angle that looks about 45 degrees, then this formula is probably not real accurate if it actually twists that much. But the formula that we came up with, so this is one we did Friday. I'm not going to go back through and rederive it. Go back look at your notes from Friday, or if you were not in attendance on Friday, you can go back and watch the video and you'll see how I derived that. But do remind you that, again, this is only valid for small deformation. If you were looking at, because we use Hooke's law for shear to derive this. So if you looked at the shear strain diagram for that particular material, it would have to be in that linear region, which is, again, we're talking about small deformation. You get big deformation, the stress is going to be larger. Hooke's law is not valid anymore, which means this formula is not valid, right? But in reality, in the real world, we're going to see small deformation. But this is the formula. T is the torque. L is the length of the shaft. J is the polar moment of inertia for that cross-sectional area. And G is the modulus of rigidity, or the shear modulus for that material. And we're going to see, just like we did, if you've got, I mentioned this a minute ago, where we had if you had the shaft that had different axial loads, right, to get the total deformation, right, you had to sum up PL over AE gave you the deformation in each section. Right? So you had to break it up and look at each section, get P for that section, or the material changed or the cross-sectional area changed. Well, the same thing is going to apply here. If the torque or the the cross-section or the material change, we're going to have to do a similar thing. If we want to get the total angle of twist, you're going to have to sum up TL over JG for each section. So instead of like different axial loads, maybe we've got the cross-section changes. Maybe the material changes. Maybe this is steel and bronze and aluminum. And maybe we got one torque going this way, we got a different torque going this way, and another torque going this way. You're going to have to do the same thing we did with the axial deformation, right? You're going to have to come in here and cut it, kind of like we did that first problem, because the torque's going to be different in each of those sections. The length, maybe we got, this is L1, this is L2, this is L3. J, obviously the cross-section changes, your polar moment of inertia is going to change. G is material property. So to get the total deformation for something like this, you're going to have to take, do TL over JG for section 1 and TL over JG for section 2 and TL over JG for section 3. You have to get the angle of twist for each section and add those up. Now, in order to do that, this is going to force us, we've got to define a positive direction. And that's something I did not mention. So that I want to go back and clarify something in just a second. Here, we're going to have to define which direction is positive. And that's what we'll talk about at the beginning of class tomorrow. But I wanted to go back. I'll just stick it down here on the bottom. So here, we're going to have to define a positive direction. Right? 'Cause one way is going to be positive, one way is going to be negative, right? It could go, you could twist two different directions. One's positive, one's negative. But when we were doing shear stress, that really wasn't necessary, and that's why I didn't do it. And I didn't think about it till now, because here we're going to have to. But just just make note here for shear stress, tau, TC over J. We typically don't define, plus or minus. When we did normal stress, there I told you, yes, you need to differentiate between tension and compression. That's because a lot of materials behave differently if it's in tension or compression. You could have buckling if it's in compression. So that's why it was important to do so for normal stress. For shear stress, it doesn't matter. If the shear stress is one way or the other, it really does not matter at all as far as the material goes. And so there's nothing to be gained by, that's why typically you don't ever see negative shear stress. It doesn't mean anything. Positive, just always usually refer to shear stress as positive. There's no need to differentiate between positive and negative shear stress. All right, does that clear? Does that explain that okay? Does that make sense? And when you're doing shear stress, it really doesn't matter. Plus, minus, just give all the stress as positive. But when we're talking about the angle, it does matter. Because if you rotate, this way, that's different than rotating that way. And so we got to define one direction or the other as positive. And that's where we'll start tomorrow. We're going to apply this formula for angle of twist and see if we can calculate some angles. So that's where we're going to stop. Any questions before I stop recording? All right, so I'm going to stop recording. And as always, if you've got a question about something, you can stick around and I'll be glad to take care of that and try to answer your question.